Hey everyone, today we will design and build together from scratch a quantum simulation software. We'll start by designing a measurement routine. So you can use this tutorial to write your own code to perform quantum measurements for any given system of any number of qubits. This is the beginning of the new year, and I just came back from the gym and I went for a walk in this freezing weather to refresh the mood. We will learn how to design the algorithm behind a typical quantum measurement routine in any code. So first I'm going to open new text files using NVim called measurements NQC. I love text files because I can write in them a beautiful text that mimics beautiful code basically, and also they can survive for a very long time. So the question is how to perform the measurements in quantum computing. So assume we have a 2-qubit system. How we can perform a measurements for a particular qubit of this 2-qubit system or any multi-qubit system. The second question is also how to measure a quantum state represented or expanded in this 2-qubit system or multi-qubit system projected in a particular computational basis, for example. So let's assume we have a 2-qubit system. So the number of qubits is basically 2. And the size of the Hilbert space of these 2 qubits will be 2 to power the number of qubits, which is 2, and then we will have 4. Which means we can expand any given state of this 2-qubit system in 4 computational bases. This computational basis constitute or form this Hilbert space. The computational bases are ket of 0, 0, ket of 0, 1, ket of 1, 0, ket of 1, 1. We need to note that the way we are writing now these kets is done in Big Endian convention. This is a textbook convention. Yeah, that's if we wanted to write them in Little Endian convention, the 0, 0 will stay the same, but then we'll count from left. So we'll have ket 1, 0, ket 0, 1, and then ket 1, 1. And this will be the Little Endian convention. Little Endian convention, it is by default used in IBM Qiskit convention, and it's more natural for computer science perspective. However, Big Endian is more natural for physics textbook perspective. So here is now the logic behind the convention. What we call as a big endian, it means that we basically put the starting or the count of qubits from left. So we have ket qubit 0 and then qubit 1. So we count from left. On the contrary, in little endian, we count basically from right. And as I type here in big endian Q0, it is the most significant bit. However, in little endian, we count from right, which means that Q1 is the least significant bit. This is very important when you perform or when we perform matrix multiplications and also perform the tensor operations. So let's assume now a general quantum state psi and this psi will be expanded in this 2-qubit Hilbert space system. So we'll have ket psi equal to A0 0 ket 0 0 plus A01 ket 01 plus A10 ket 10 plus A11 ket 11. And we need to keep in our mind that this is done in big endian convention. The kets 00, 01, 10, 11. These are the computational basis of the 2-qubit Hilbert space. The coefficients A00, A01, A10, A11, these are the complex coefficients of the quantum state psi. And from that we can get the probability amplitude to find the ket psi projected in each one of these computational bases, as we will see in a second. any quantum state in any Hilbert space should be normalized, which means that given kit psi, that means that within the sandwich integral rule or Born rule, the projection of psi with itself, if we perform that, we should get 1. And this is numerically is translated that the sum of the squares of the complex coefficients should be equal to 1. Then now we come to the measurements and how we can perform in principle the measurements. And the answer is we can perform in principle or typically 2 types of measurements. First, we can measure a given quantum state in a particular basis. And secondly, we can also measure a state of a particular qubit in a multi-qubit system. Of course, in a given computational or particular basis. So first, let's consider the case of measuring a given quantum state in a particular basis. For example, if we have the kit psi equal to A11 kit 00 plus A01 kit 01 plus A10 kit 10 plus A11 kit 11. And we wanted to measure how this kit psi, when we do the measurement, we found it projected on a given state or dimension in the Hilbert space. So what is the probability to find, for example, kit psi projected in the dimension 00, or in the dimension of kit 01, or in the dimension of kit 10, or in the dimension of kit 11? So here I copy the definition again of kit psi expanded in the computational basis of a 2-qubit system in Big Endian convention. And if we perform the measurements, we can find the state in any one of them, either here in within the dimension of ket 00, or here in the dimension of 01, or here in the dimension of 10, or n11. And of course, we are measuring here in the computational basis. And here are the 4 probabilities. So if we do the measurements, we can find that the probability to find the ket psi in projected in a particular basis will be the squares of these complex coefficients, which means that if we do the measurements 1000 times, the number of times we find the state 00 is basically 1000 times the probability of ket 00. And similarly, you can find the other the number of measurement where we can find state psi projected in 01, 10, 11 using a similar approach. Also, we can perform the measurements in a different basis. To understand how to perform measurements on, for example, different bases, let's having a look on the Bloch sphere. If you open any Bloch sphere, you will find that there is X, Y, and Z, and for every axis we can have a specific representation for the basis of a qubit. So in principle, we can perform the measurements on the Bloch sphere in any direction. Basically, for example, in X, Y, and Z, because also we can also perform the measurements in any arbitrary direction. However, if we got the 3 dimensions, we can perform first a measurement on the Z-axis. That means we measure a qubit in the computational basis of Kit 0 and 1. This is why it's obvious why it's called computational basis, because it's composed of zeros and ones. The one corresponding to the gates in conventional computing. Or we can perform the measurements on the x-axis, which mean that we use Hadamard basis, basically plus minus basis. Or we can measure it on the y-axis, which means that we perform the measurements on what's called left and right basis. With regard the computational basis as a fundamental layer, of course, it's a matter of perspective. In that sense, we can express the other types of bases in terms of the computational basis, and vice versa. We can also represent the computational basis in terms of Hadamard plus minus or left and right basis of the y-axis as well. But let's express everything in terms of the computational basis. Hence, we can express plus and minus in terms of computational basis as follows. So the Kit plus will be 1 over the square of 2 times the sum of Kit 0 plus Kit 1, and similarly Kit minus will be 1 over the square of 2 times the sum of Kit 0 and the Kit 1. Sorry, the subtraction between them. So it will be Kit 0 minus Kit 1. Similarly, we can express the basis of y-axis in terms of plus minus. So we have Kit L will be 1 over square root of 2 times the sum of Kit 0 plus I Kit 1. Similarly, Kit R will be 1 over root square of 2, the difference between both. So we will have, was of course including the imaginary number. So we'll have Kit 0 minus I Kit 1, where I is the imaginary number, which is the square root of minus 1. Using this simple transformations, we can perform the computation in any type of basis on the Bloch sphere, basically. And this type of measurement is easy, as you see. We just only need to adapt this particular relations and this type of measurements in the code. And this is very straightforward because we can just translate what is written in the nodes in the code, basically in the language you prefer, like Python or Julia or presumably Fortran or C. However, in high-level languages like Python and Julia, you can just type similar syntaxes similar to these nodes. You can just type them and perform your computations. We have done this also in our own package, which is Molkit. You can find these measurements. It is an open source package with MIT license. Please follow the information on www.molkit.io. Now we move to the second type of measurements, and this is the fun part. Typically, we have questions like how to measure a single or a particular qubit in a multi-qubit system. And here I copy again the definition of KIT-SCI. Of course, in big Indian convention. And in order to understand the notion of measurements of a particular qubit in a multi-qubit system, let's assume or consider the following scenario in which we are interested in measuring the first qubit Q0. And of course, we have to be careful about the numbering from which qubit we start. So what we mean by qubit, first qubit is just the qubit 0. So now this particular qubit, if we measure it, we can find it either in state 0 or state 1. And now let's have this question, where we can find the first qubit Q0 when it has a value of 0. So for example, let's assume that we perform a measurement and we find it in state 0. So where this particular qubit Q0 has state 0 expressed in the given quantum state. So of course we can find them in the first two terms. So I'm writing here a small tip that we also can understand the measurement from the position of the qubit in the tensor product. So if we have the KIT 00, it means that we have the tensor product of KIT 0 multiplied tensorically by another KIT 0 of the second qubit. and this is the answer. You can find it in ket 00 or ket 01, which means in the first two terms in the psi state expression. And if we measure the first qubit Q0 and found it in state 0, then the whole state psi will collapse, and we only will end with the terms or the bases in which the first qubit Q0 already has a fixed state, which in this case is a 0 state or ket 0. Hence that means that we will have a state of psi prime, which will equal to A00 times ket 00 plus A01 times ket 01. We must take care, of course, that this function or this new function, the function that's produced or the outcome of the collapsed original state function, is not normalized. So we have to renormalize it. So let's call the new normalized state psi prime underscore norm, which will equal to n times A00 ket 00 plus A01 times ket 01. And n is a newly introduced normalization constant. We can have an alternative scenario where if we do the measurement, we find the first qubit Q0 in state 1 instead of 0. And then the state function will collapse to a new state called the psi double prime. And in this state, only terms where the first qubit Q0 has a fixed state, which is ket 1. This one will be the surviving ones, and these will be the terms of the newly collapsed wave function or state function. Of course, it is not normalized, so we have to renormalize it using the constant n. Yeah, sometimes the copy feature doesn't work properly. However, it works now, so that's nice. Then it doesn't work, so let's just try to type it by hand then. And of course we can measure qubit Q1 in the same approach. However, instead of tracking the position of the first qubit Q0 to see where it is located, we will now trace the second qubit, which is Q1 from right, and we will look to its own state, where it is of a value 0 or state 0, or and when or where it has a value 1. And with this, using similar approach that we have done for Q0, we can also define the states in which if we measure Q1 to find it in 0, the wave function will collapse and we'll end up having a new state function, psi prime. And similarly, if we find it in kit 1, then we'll have a new collapsed state function where the terms or the surviving computational bases will be the ones with in which qubit 1 is equal to 1 or has a state 1. Here let's explore a numerical example where if we given the state psi and then we have the coefficient of half, 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 that state could be achieved by applying the Hadamard gate twice. First on the first qubit and secondly on the second qubit. So we typically assume that the quantum register is initiated in the zeroth state, which is kit 0, 0. And then if we apply Hadamard gate twice, firstly on the first qubit and secondly on the second qubit, and then we achieve this particular mix or a superposition of the computational bases kit 0, 0, kit 0, 1, kit 1, 0, kit 1, 1. Hopefully now the function of the mouse works fine, smoothly without any issues. Yeah, great. first we need to measure the first qubit Q0 to be in a state of kit 0, and for that we have to locate where Q0 has the value 0 in these given expansion and computational basis. And of course this lies in the first two terms, ket 00 and ket 01. And of course if we find first qubit 0 to be in ket 0 state, those are the probabilities to find it Q0 to be in ket 0 or Q0 to be in ket 1. And that's if we assume that if we measure the qubit 0 and we found it in the state 0, then the state psi will collapse and will becomes the state psi will collapse and it will become state psi prime, which will equal to half times ket 00 plus half ket 01. And this is a little reminder that we are still in the big Indian convention. Of course, state psi prime is not normalized, so let's normalize it. And the normalization can be done by multiplying the normalization constant n times the survived terms in which Q0 is in a state of ket 0. And similarly, we can measure the state of Q0 to be in state 1. Then we get a new state, psi double prime, after collapsing of the original state function psi, which will have the surviving terms in which q0 is in state 1, and of course it is not normalized. Then we have to renormalize it, and then we introduce psi double prime underscore norm, and this is the way we renormalize it basically. And of course, we have a newly collapsed state. And this will be the newly normalized state. So now after the collapse of the state function into the new psi prime normalized, so after collapsing the state function, we get psi prime, that's turn out to be expanded in the terms get 0, 0 and get 0, 1, based on measuring the first qubit q0 and finding it in the state get 0. We can also carry on and continue applying for example another gate or operator, and then we can measure q0 again, or even measure the other qubit q1 using the same approach. And of course, since the Hilbert space is composed or based on 2-qubit system, once we measure the second qubit, for example, Q1, or do a second measure to the first qubit Q0, the whole superposition is destroyed, and then we will end up with a fixed value and a fixed computational state. And this will be like with a probability 1, so we'll find it all the time. Now let's follow a different approach. So let's measure the second qubit Q1 after finding qubit 0 in state 0, and we go with this particular scenario. So if we look to qubit Q1, we can have two possibilities. It could be in state 0 or in state 1. How we would know this? Because if we look to the left terms after the collapsing of the state function after measuring the first qubit, we have the two terms ket 0, 0 and ket 0, 1. And if we look to the second location, which is the location of the second qubit, we'll find that the second qubit Q1 could have two values, 0 or 1. And hence, let's rewrite psi prime normalized, which is a collapsed state function after measuring the first qubit and finding it in state 0. That will be 1 over square root of 2 ket 0, 0 plus 1 over root square of 2 ket 0, 1. And then if we look to the second location for where is the second qubit is located, then the second qubit Q1 can have either the value 0 or 1. So if we find that the second qubit Q1 is in a state 0, that means we will have a fixed outcome of the measurements all the time, and this will be the ket 0, 0. And similarly, if we find the second qubit Q1 in state 1, then the whole system will collapse and we'll have a fixed outcome of them for the measurement, which will be ket 0, 1. And then a state vector simulator, we can do this as well and take care of the random assignments of having either 0 or 1 for Q0, for example. And based on this random assignments, we continue in these scenarios, whether we go for a second measurement for Q0 or we measure the second qubit Q1. And hence, this is how we would perform the simulation for any number of shots, basically. that's it for now. Thanks for watching this tutorial. If you like it, please do like and subscribe to the channel, and if you have a comment or a feedback, please write it below in the comments, and see you next time.